And the recording has started, and allow me to formally, introduce, my dear friend, so Professor Curet. So Professor Curet, is currently an associate professor in the Department of Ocean and Mechanical Engineering at the Florida Atlantic University. He completed his PhD and a master's degree in mechanical engineering at Northwestern University, and his bachelor of science, also from mechanical engineering from the University of Puerto Rico. And before joining FAU, he was a postdoc researcher at Brown University. He has a very broad, research interest, focus in different areas of bio-inspired systems. Maybe you guys have seen some traveling wave propulsion with focus in fluid mechanics and marine propulsion, multi-agent system, energy harvesting. And today, I guess he will talk about coastal protection. His research has been funded by multiple agencies, including NSF, and ON Office of Naval Research, and the Joint Research Foundation. And particularly in 2018, he was awarded an NSF career. With that, the floor is yours, Oscar.
Well, first of all, Dician, thanks so much for the introduction and the invitation for the talk. It's a great pleasure to share my work, which is actually, you'll see, it's really most of my students' work, and I'm just presenting. So as Dician mentioned, I'm going to talk a little bit about fluid dynamics of Mangrove-Inspired structure and its potential implication against erosion and again, coastal protection in a more general way. I'm associate professor here at the Department of Ocean Mechanical Engineering for Atlantic University. And so let me start, talking a little bit about mangrove. Many of you might be related or familiar, but some of you don't. So mangrove are really the interface, the natural interface in subtropical and tropical region between the ocean and land. And again, there are different types of mangrove. I'm going to be looking more at red mangrove, and they could as well, you will see in a moment, they could grow in different scenarios. Could be basically open to the ocean in coastal regions. And so as you might know, there are different types of mangrove. Red mangrove, it's usually closer to the ocean or the water. Then we, of course, we have a black mangrove, white mangrove, and they tend to be a different distance from shore. These are the most common mangrove we'll see in South Florida, but there are probably hundreds of species. These are the most common one that we see here. And you will see red mangrove, they are very peculiar structure. You can see that on the red right side, bottom side. So these are very interesting, peculiar structures that kind of extend radially from the center of the tree, and they extend in different regions. And that's the one that are most common in South Florida, and also they're closer to shore. But of course, we have black mangrove a little bit farther away from shore. We also have white mangrove. And this is just overview of the mangrove distribution. You'll see of course they are they have to be in the tidal zone, and they're predominant vegetation at the interface between land and our coastlines. And there are very few actually. They live in a very harsh environment. Salty water, interaction with wave, with flow. There are actually very few species of vegetation that can grow in those conditions. So that's one of the things that got interested to me. You have these trees specialized at that condition, at the interface. which we could learn quite a bit from them to maybe get some inspiration, not only to understand the fluid dynamics, but also how we can use their structure as a resilient example for coastal design, coastal structure. So I first of all, I want to be clear, mangroves are very complex. This talk or the work that I'm looking focus more on a single mangrove tree. And I saw before, even a single mangrove tree is very complex. A few years ago, we tried to do laser scanning, and it's very difficult. It's very difficult. I mean, at some point we retake that, but some of the work that I'm going to present here are models that are, of course, a simplification of the structure. But still, I think with those simplification, we could still understand some of the basic principle. And even though I look at mangrove right now as a single tree, I don't want to minimize their complexity, the different interaction. You really see mangrove more generally in a forest. So mangrove forest can classify depending where, there are different types. There are a few of them are shown in the in the right side. You can see this fringe mangrove forests that are really like a borderline. And again, they are red mangrove are very common in this type of mangrove forest. You have basin where everything kind of flooded. Red mangrove are not typically in that arrangement. You have also riverine type of mangrove where you have kind of constant flow in that region. We have also the overwatch. There are, when in high tide, everything is completely submerged. So this is common in small islands or keys that are basically built from mangrove. And again, red mangrove are common in this type of forestry. And then you have the dwarf. These are technically any species of mangrove could be dwarf. These are most common in really harsh, really high level of salt water, not too much fresh, so they're really small. Now, there's a lot of complexity on these mangrove forest. And although, I would like to at some point address some of these complexity, this talk at the work that I've been looking is just looking more in a single tree and a patch of, root trees. And you'll see some of the simplification. And of course, as we evolve and we learn more about that, we can explore more complex scenarios. So why mangrove, and what do they, why they're important in so many cases? So you will see that, we are very vulnerable in some ways, coastal population, from hurricanes, tsunamis, effect of sea level rise, water quality, sustainability of energy, fishery. And I think mangrove could help in many of these areas as an example for resilient structure, to protect coastline, to help in erosion, and also improve, in so many cases, water quality. They're really pressing pressing challenges that are not, won't be easy to address in some way. And this challenge of that, it's in some cases the scale of the problem. You'll see the erosion happening and the loss of the sandy beach. In so many cases, we want to address this. Our rethinking approach of engineering might probably change because maybe not feasible just to, build coastal structure as we are usually doing, just because it's at the scale and how large it is. So you will see in recent years, you have seen these engineering approach to natural system, looking for oysters, for natural filters in the New York Bay. You see living breakwaters with oysters project, and all these kind of, appeal to the to how we are, how we approach this problem. Okay, and similar way, I was looking at this solution. Mangrove could help us both as a engineering model, but also how important it is to preserve their ecosystems. So mangrove, I just gonna give a little summary. There's, again, not gonna go in detail. I'm not a biologist by training and mechanical engineering, but I can tell you there's a lot of benefits of mangrove at different levels. You go from habitat, they provide ecosystem for fish, oyster, really important bacteria, fungus. So that's one very important aspect. Also, erosion control, as I told you, they actually the interface between ocean or shoreline and land. They're very important to control sediment deposition, particularly to very fine particles. Sometimes it's really difficult with current system to help the sedimentation of these sediment particles, and mangrove are actually very good at that. Of course, you can see wave mitigation, and you can see so many cases have been documented how they can help in against waves, cyclones, tsunamis. So that's one thing. Well, another important aspect that sometimes is people are not very aware is that actually mangrove are key for CO2 capture. They are not only as the tree itself, but also their ecosystem that they create. With their bacteria, fungi, they are able to actually sink CO2 they are dissolving water and keep it on the sediments. And again, this problem of sea level rise and CO2 levels of acidification, mangrove could be in some ways a very important system to look at. So, and you might be aware there have been a reduction of mangrove in the last, a century. We have a lot of development in coastal structure, at least in South Florida, at least Miami area was basically all mangrove forest. And of course, many of these areas have been removed by seawalls. And now one of the questions, one of the things that we could do is how we can either, bring back mangrove from those areas, or how we could create structure that replicate that, but not only replicate their structure, but also that they can replicate their functions. Okay, and hopefully in some way we could use that to replicate some of their functions that they provide, including CO2 capture, wave mitigation, erosion control. And this were actually, I started interested on this I met an architect a few years ago. He was looking at ocean structure and was looking at mangrove. And he has some different design of seawalls. You can see in the bottom right, he has done few seawalls designed by mangrove. And after talking with him, I really got interested on that and the importance that they have. And he was more interested on the, the fabrication aspect, on the design aspect. But I thought that, there is a little bit of a gap on how we understand the fluid structure around these routes. And that's how I started this project. And actually he has few panels in South Florida looking at Mangrove-Inspired seawalls. And again so these mangrove walls, they are not only one of the interesting part is not only the structure that mimic their roots, but in some ways the functions that they do and how they can interact with the ecosystem. So you'll see in many cases, this figure here, you see these are actual mangrove roots, and they have this relationship with oyster. You see that these oyster balls grow on some of these mangrove. In this right side here, these are actually a seawall inspired mangrove. And one interesting thing is that we see as well these growth in oysters, which actually are very important as well for water filtration. So this is, this interesting relationship between the shape, the function that they can do, and how they can interact with the ecosystem is something that in some way I'm interested in. The fluid dynamics could help to design some of these structures. Now, the fluid dynamics of mangrove roots could go different scale, right? You can go from, the microstructure of just the roughness. You could look at one single root that is, just few centimeters, to one tree, to a forest itself, right? So you have very small scale full interaction, but you could also have like implication at much larger scale, looking at kilometers length and how that can affect your ecosystem. So in many cases, I'm just for this talk and my work, we are just focusing right now in the few roots. Okay, so we are not trying to make the case that we understand the larger scale, but at least having a bit more knowledge of interaction of few of these roots. And I want to say by some of the roots that I'm looking at some way a little bit simplified model. So you will see most of the work are a collection of rods. Many of them that we do are wood, but some of them we 3D print them. Okay, so most of the work is just straight, and we have looked at different ones that are more complex, but most of my work is looking at simplified models. And as you might see, this is not, I'm not the first one looking at this type of work. There have been quite a bit of work of similar vegetation models from, NEP that is here. You have Mazda, and even though you will see some similarities on some of the fluid structure that I see, not only with these type of models, but also with seagrass models, and there's some similarities with this canopy type of model. So I just want to say that this is given in a context, and I don't want to say that I'm the only one working on this. There is a lot of similarities and things that we learned from previous work. And this is just a selection, not a very extent work on that. So one of the first things that I want to do is before looking at actual measurements, we try to understand or look at what is the flow. And one nice way to do this, you might be familiar, it with soap film. So if you're not familiar, the setup is it's quite a bit simple, but also could give very nice result, and you can get a lot of information just from flow visualization. So what we're looking in the left side is just one snapshot of a video. The right is just like schematic of the setup. We have gravity is going down. We have a reservoir. We have an overflow with a constant pressure head. We have a valve that we can control. We have a nylon that we extend, and somewhere in that we put our model. So our models are just like a cluster of cylinders, and And the water here is just a combination of course, water, soap, and glycerin. Okay, so to avoid evaporation. And then we see where everything is going down, so it's like a film. And here just a video of that, what's going on. So it's actually very interesting. So you'll see, you see some vortex, some flow structure interaction at a small scale, and somehow these small structure does interact and actually gave rise to a larger vortex structures. And here's just a close-up view of that. You will see, those vortex shedding from here and also from the small cylinders and how they recombine later on. And we did different experiments looking at different models, going from a single cylinder that you see on the left side. When I say porosity 0, means that there is no water inside that model. It's completely solid. The blockage, there is nothing flow can go through that model. And then when you see 90%, it's like 90% is really inside the model is water. And you'll see different, different cases we test for 30%, 70%. And, you could see some of the structure here. Something that is interesting is like, when you change the porosity, although you see very similar structure, you see the vortex just the wake behind, slightly different. Also, you see the spacing between the vortex structure getting closer. So that means that the frequency of the vortex shedding is increasing. We'll look at that in one moment. And again, this is another flow visualization. In this case, it's a little more complex. You could see the bleeding or the flow going through this model, which is shown here in the right side, and we'll see the flow is passing through. You have some vortex, structure here, but everything then later combined. This is again have been reported for different other cases. So let me just, and then so what we see here is what being reported in some other similar models. So we have if this is a very simplified schematic, so you have a model that the length scale of that is like D, like your patch diameter. We have the roots diameters, small d, and you have a space in between them. So what we see is like you have this small vortex structure that they do, are generated by the small diameters, and they do interact, and they give rise later to a bigger vortex structure. So with that, we went to try different models, but are now in a flume. So this is in the top left. We have a picture of our setup. We have a model is composed of many different rods. We mount everything in an air-bearing system. We measure forces, and also behind in this particular experiment, we did measurement with a vectorino, just point of the flow measurement behind the patch, and also we did some PIV experiments to measure the flow in a plane behind that. And the Reynolds number, just to give you a range, we look between 2,000 to 11,000. And this is just looking at the D or the patch diameter as a scale, the length scale. And I think I did make a mistake here. It should be a D instead of L. So we tried, we the different different cases. In this particular case, we have the same number of rods. They have like, I forgot, I think they're at 50 here. I really forgot how many we have, but they have the same. They have the same arrangement. We only change the small diameter between them, and as we change the diameter, what we call porosity, or the volume of water inside that model, divided by the total volume, is changing, right? And you know, when you have bigger diameters in the roots, you have a smaller porosity or larger blockage. And then you have case 4, for example, the diameter of the roots are very small, so there is very small blockage, but really high porosity, right? And and these are cases from the Vectrino. So just 1 point, just behind that, just in the wake, in the midline where X is, and we look at this measurement at a different position, and this is our incoming flow. What is showing these figures: incoming flow divided by normalized by the stream-wise velocity to infinity, and you know, and some of these have been, you know, shown in other cases. We see similar things. You have a like really high blockage, case 1, for example. So you have like a really deficit in your speed. So you see like a negative flow behind that model, and then it quickly goes up, and then as we move away from that model, it kind of switches back to the streamwise velocity. And as you increase your porosity, that means that there is less blockage. That's deep in your flow deficit decreases, means you have less, you know, negative value, or, you know, so that deficit is less, but the length where it's occur is longer. Okay, so we could also use L1 as our length scale to determine where is this wake region of the small vortices. And if we measure that one, we could have this L1, what is shown in the figure at the top, normalized with Z, change with porosity. We see that as the porosity increases, of course, this wake region, or this L1, it does increases. And as I told you, we have done different PIB. And well, what is interesting is, like, you know, actually the flow, I mean, if I don't tell you that this is like a composition of patch of different cylinder, this is very similar to like a single, just like a solid rod. You have many very key similarities, right? So you see the Porosity structure, they are shed, and it's in some way it's similar. However, as we change the blockage, so these are again time instance of vorticity. For high blockage, 47% porosity, and then as the blockage decrease, of course, this vorticity level decreases. However, they seem to be extend farther away. Okay, and here I'm showing, you know, this is the same PIB data, but instead of time instant, I'm looking at the time average flow. So in the top row, we have the stream-wise velocity normalized by the incoming flow. And then we see for 3 different cases, high blockage, 47% porosity, to low blockage, or 86 porosity. And you will see it's evident here that, you know, for like high blockage, the 47, you see a really strong deficit in the wake, but a more shorter region. and then that could, then you could play with that depending on your porosity. And you know, the question becomes, you know, how you can use that, how can Mangrove use that to affect your flow, okay? Now in the bottom, in the bottom row is actually same cases, 47, 70, and 86, but looking at vorticity, and again, this is average vorticity. So you'll see high blockage, you'll see really strong vortex in the top and bottom side of the model, with a shorter length tail behind the model. And as we increase that porosity or less blockage, the vorticity level decreases substantially, but the length also increases. Now, I mean, as you might know, you know, we could look at some of the characteristics of this dynamic flow. Can be look at the Struhel number, and for the region that we are looking at, for 2,000 to 11,000, you know, it's the Struhel number is around 0.2, right? And that's what we look at, and it's fairly constant. Okay. Now, if we look at the Struhel number from our cases, actually, they are not constant. They are changing depending which porosity you are using. So in this graph, I'm showing in the x-axis, this is the Reynolds number, basically. And Reynolds number is being changed by flow speed. And then we measure Struhel number just behind the wake at a few diameters behind. And then you'll see that the Struhel number is fairly constant for a different Reynolds number, but they are changing depending on porosity. So it could go to, you know, a little bit less than 0.5 for 80%. Then they go to 0.3 for 70%, and just slightly like 0.25 for 47%. So this is a very different from a cylinder. So in this case, actually changing your porosity, changing those, is highly affecting our Struhel number. Now, one thing that we try to do is like, you know, could we define another length scale, which we call effective diameter, okay? So instead of looking at the patch diameter itself, it's like, could we define another length scale based from our Struhel number? So what we did is like, well, if we set our Struhel number around 0.2 as you know, as a cylinder, as a solid cylinder in this Reynolds number has, could we get, based on the Struhel number we had, what will be the effective diameter? So that is actually 0.2. So so what we found is basically that as you have higher porosity, that means less blockage, your effective diameter, it's smaller and smaller. So you could see here, it's the effective diameter versus porosity. So in y-axis is porosity, so you can see less blockage. And then in the y-axis is the effective diameter over d. So as you imagine, at this porosity go to high blockage, that means you know, zero porosity, you know, that should be equal to 1, okay? But as you go higher porosity, less blockage, you know, that represents like a much smaller solid cylinder. That's what it's basically saying. And it seems that, you know, we have relatively constant result for the different Reynolds number that we look at. Now, if we look at now that, because one of the questions always becomes, you know, if you have all these length scales, what is actually your length scale to use? Is the patch diameter, the root diameter? And of course, it really depends what you're looking at. If you're looking really next to the roots, so you probably use the root diameter. But if you look at that farther away from that, the question becomes, what will be the appropriate length scale? And we try to use different ones, and we got reasonable result if we use effective diameter to collapse our coefficient of drag. So here is again Reynolds number. I now define not with the patch diameter, but your effective diameter. And then getting your drag coefficient, again, based on that effective diameter. And, these are the different data we saw. It's a little bit scattered, but still it seemed to follow some sort of common trend. Now, we can also see how this, we could define a blockage area, how much based on the effective diameter, that will be your drag coefficient times your frontal area times diameter. This is everything effective, and how much energy is released per one vortex shed. And, that basically saying that your higher your blockage area, as we expect, is a higher energy release. The energy release is based on really on your vortex shedding. And what is interesting that they seem to follow like a common trend, like a monotonic common trend. So I'm going to switch gear right now. We, just so far be looking at some of characteristic of the flow. But something that I was interested is also, what is the effect of this patch on erosion? Again, these I'll be looking at different cases for seagrass or different other structure, but I'll be looking more. These want to focus is again on mangrove, in the right side you see some of the mangrove in some of the canals here in South Florida. You see some of their potential effect on the erosion. Again, we these patch are going to have an effect on the boundary layer from your viscous sublayer to inertia sublayer. And one thing that we did is like we run different cylinders, again, going from was single cylinder, there's no patch, and now one with same outside diameter, but just changing the root diameter. Again, you go from 0% to 86%. And then we fill the flume with PIB particles. We let it run for a few hours. And then after that, we took picture of the deposition behind all these models. And what you see in the figures are really deposition after a few hours of running. And what's interesting is that, it seems to be that if you have really high porosity, less blockage, there's very few particle deposition there. And then it seems like at some in case 2, like 47, you have a really higher deposition compared to just a single one. And one of the things that we want to do is like understand a little bit more why that might be happening. And again, there are very different factors involved here. And in this graph, we measure the deposition area. That's basically mean like, we're not looking at really at the quantity of deposition, but just like the how much we see area of this deposition, okay? And again, in the y-axis, we have different velocities. In y-axis is the deposition area that we found. And the different symbols are different, the different porosity of the models. And we could do the same, we can replot this same graph, but instead of looking at velocity, in this case, we have like a porosity in the x-axis. And what we saw is like, at this case of 47% porosity is where we see the peak. And something that I didn't tell you is like many mangrove, when they define porosity or when they look at porosity, it's actually around these 47% that is reported on nature. So that's why we use that quite a bit. And it's interesting that at that case, we did find an increase or a peak on our deposition area. So to understand a little bit more what's happening between these two, so we did our flow measurement. Now, instead of looking at the horizontal case, we are looking at the vertical case. And then we did streamwise velocity. These are just streamwise velocity measurement. This is average. I think I'm taking a bit too long, so I'm just gonna, gonna speed up a little bit here. So this is our velocity profiles, again, for different cases. 100%, that's a single cylinder, and the different, 100% is this. There is actually no, there is only the flume running. There is nothing else. And then you see all different cases. And 47 is the red one. Is the one that we see with higher deposition level. And we could calculate our coefficient of friction for the different cases. And what we found is like this coefficient of friction is your tau wall divided by density and U squared. We see that the coefficient of friction for this 47% porosity is the highest one. We also look at the vorticity level. So this is the vorticity behind. I know that this is only one plane and the whole system is 3D flow, but what we found also that this 47%, it seems like the vorticity is suppressed. So there's a less vorticity level just behind the patch. Finally, something that was interesting is just, of course, these roots generate some turbulence behind, or these models. So something that we found interesting on the turbulence level is that, and again, so this is turbulence is defined, in the bottom side. But what we found is that the near turbulence, okay, of the 47 is like a very low turbulence of velocity fluctuation, and that might explain, or even an insight of why we see a much bigger deposition area. And if we look again at your turbulence kinetic energy for the 4 different cases that we study, we see a drop in the turbulence kinetic energy. So this is again y-axis, your turbulence kinetic energy, and our x-axis is y plus. So we think that these there might be a viscous deposition just behind that for the 47 that serves like a sinks vorticity and also affects our turbulence levels. And that's kind of key on the process of the mechanism of deposition. That's what we believe. So just to summarize on this erosion, sorry, I'm rushing a little bit, I don't want to go too long, is that we see a low near bed turbulence with small velocity fluctuation, low vorticity and high friction coefficient, and that's really somehow the mechanism that it seems to be enhancing our, in this case, deposition of these sediments in the flow. One last thing that I want to go, so far I've been looking at a fixed arrangement, and you see one of the questions that I have, if we want to sometimes we want to go beyond these fixed patterns. We choose that because it's easier to model, to create, and so on. But what happens if we go beyond that? Not like a really fixed pattern. And that's what we try to answer in some of these work that I do in collaboration with Dr. Burma, is how we can arrange a number of cylinders. In this case, are 9, which, there are few parameters. There are 9 cylinders. They cannot be farther from this dashed line, but we can really change the radius or their angle. Okay, and the question becomes, if we are free to put all these cylinders around them, how we can optimize to increase drag just because you have more momentum, extracting momentum from the flow, and minimizing entropy. In this case, entropy as as a way to see fluctuation in the flow. So in this case, actually, we mostly look at simulation, and we are looking at multi-objective optimization, and we really are looking at solving the Navier-Stokes equation, evaluate that, and do different generation until we converge and find our optimal cases. So this is the first generation. I'm showing 4 different graphs. Drag is in the left in the y-axis. Note that is decreasing down, and then entropy is in the x-axis. And what is interesting, we start with the first generation fixed pattern, and we keep iterating and solving this to optimize. And after 33 generation, these are what we call Pareto Front or optimal cases. These are the combination that actually are these front here really represent our optimal for the increasing drag and entropy at the same time. Okay, so what is interesting, we after a few iteration, we could get much better in this in some way, and it's nothing close to our fixed patterns that we have. These are different cases, A, B, and C, and these are showing the configuration. And just to show you, these are some of the flow features that we see behind this patch. Again, we see similar structure. Before you have this small structure, they recombine, have larger, but actually we could get, depending on our space to do for arrangement, we can really vary quite a bit our drag and entropy behind that. Now, this is my last slide here. Just what is looking forward, or I'll be looking at, tell you, even though we're trying to understand more the fluid dynamics, there are a few things that are really important that we have not looked at. This is our kind of goals in some way, looking at the micro level structure of these roads, looking beyond fixed pattern or straight. You just look at the structure level, interaction between many of them, and hopefully at some point we really look at how this can interact with a complex system, looking for multiple of them, but also with ecosystem, and hopefully also understand how this could help and enhance our coastal protection and in some way economic development. There are a few conclusions. I'm just gonna go through, just look at this flow structure of Mangrove-Inspired structure. We look at waves, through whole number, the drag, the erosion, and then we talk a little bit about some of the mechanism for this erosion, and looking beyond fixed patterns and look optimal arrangement where are free to move in some way. with that, I just really want to thank my students, some collaborators that really Amir, Kasemi have the one that have done most of the experiments here, and some acknowledgement from the funding agencies. And with that, I just want to stop here and have any question if you have. Well, thank you for listening.
Thanks, Oscar. First of all, the last picture is really beautiful. So,
oh, thank you.
I just want to comment on that before, like, open the floor to questions. Like, I cannot resist just to comment on this. So, with that, like, thank you, Oscar, for this wonderful talk.
Thank you.
And,
thank you. I appreciate your attention. Thanks.
And yeah, like, let's have the audience to have questions. And
yes,
yeah, Heidi.
So I have a question. That was a lovely talk. Thank you. Very clear and
Thanks.
Lots of good connections. So my first question is, so you observe that there's lower turbulence at the bed for 47%. So I could see why lower turbulence might lead to more deposition in a volumetric sense, but you are measuring deposition in an areal sense. So yeah. Did you actually map? Did you do a map of the spatial distribution of low TKE and map it spatially correlated to the spatial deposition pattern?
Actually, we that is a good point, and these measurements are in a midsection, so we don't have a map in the horizontal plane. We are just looking at a single plane. So you see, I think that's something that we want to do. Like you see, let me show you really quick. I don't have the setup. Oh, no, here it is. So our field of view, actually, don't look at the C one, is actually this is the plane we're looking. It's just the midsection below. You could
certainly do slices in different lateral positions.
That is correct.
I feel like that would be really give a much stronger relationship to saying the area of the deposition to map, because, and my other question to follow up on that is, why do you think the turbulence is lowest for that scenario?
Well, I mean, we're looking at, again, so with the caveat, we're just looking at that plane, right? So I do understand we could replicate or run these experiments again at different planes, and that's something that we have the capability. We have not done it. So we are looking at our see what we have. So
yeah, see, I got confused because it says XY. That's not the XY plane.
Where?
So why is vertical in your domain?
Why is yes, yeah.
Okay.
So that's. I mean, yes. I think that's that's correct. I mean, I would probably have to see this to be more conventional. But Y in this case is a vertical direction.
Okay.
And X is stream Y. And so what we found here, so this is just more on the vertical plane. And what we found is that our turbulent kinetic energy it's lower at in the 47% compared to any other cases. Of course, we have just few cases, right? So we haven't looked. That definitely we could explore again more of this porosity, but we have not done.
But do you have any insight as to why this porosity is producing the low turbulence at the bed?
Yeah. Now that question is why this is happening. No, that's interesting. We don't know. Like, to be honest, we don't know. Like, why will this give rise to a lowered turbulence? I don't know. I mean,
okay, all right. So that's future work. That's future work. Okay.
Future work. I think
future work. Good. Good. Okay. And then my other question was, are you familiar with the work of Nicole and Ames, 2011? You might find that to be a useful comparison. If you haven't seen it already, I could send it to you.
Oh, that would be great. I mean, I think it seems, where is it? I mean, I think it seems, you could send me, you could send me that. I've probably seen that paper, but it doesn't.
Yeah. Ian Ames, he's at, I think he's at University College of London. He's did similar configuration, but in only numerical simulation.
Okay, I see. Got it. Okay.
Yeah, so I think it would be a nice complement to your physical.
Okay.
Yeah.
Okay.
But anyway, thank you very much. I enjoyed that.
Thank you. Thank for your, thank for your question.
Okay. Autumn?
Hi, I really enjoyed the talk. I have a few questions. So I study black mangroves. I'm Heidi's graduate student, so I'm not as familiar with red mangroves. And I was wondering, how did you pick the 9-cylinder? Like, why 9 cylinders for the arrangement? Is this like an average number of prop roots per mangrove in your study site in Florida?
Well, for the last one, we used 9. I mean, we have looked, our first, let me say, let me just one second, because we had some experiments first that we did that are not known. So we have looked at much longer, larger flow, and we compared this one with the 9 one. There are some, we could understand some of this relationship between 9 or much longer. I think it's just in some cases there is no like, I cannot tell you why. It's just there is not really like a good answer why we did that. We just look at different cases from like many cylinders to 9. They do share similarities, so in some way it was somewhere simpler to set up in the sub film and then continue that work. So I think it's like to be honest, I think we start in the sub film. So when we look at sub film, which is we have very limited flow, so some of these actually we start with 9. We could not do very big, and we start like that, and then we keep really focusing on that in some way for the PIB and the force measurements. But and this last one for erosion, we keep 9, but again we have done it for different cases of number of cylinders.
Okay, and typically is the main trunk the same diameter, like similar diameter to the prop root diameter? Like the center dowel in like an actual red mangrove, is like that center like supposed to be like the main trunk of the tree, or like are they typically like
they do? Like the same diameter? Let's see if I have like a picture. It's sometimes really is they do change a little bit. So this is like, let me see if I can zoom in here. They do change. It's not the one in the center that's slightly bigger one. It's not like I don't think it's like an order of difference. So it's not like like a one order of difference. They are similar, but the one in the center are usually bigger. Just for simplicity, in our case, we kept the same. But definitely something you will even see from that one here. So you see that one is slightly bigger than the one that they protrude from here, but same thing will be from the center one. Center one is usually a slightly bigger one.
Got it. And then my last question is, when you were showing like the setup for the soap film, what are the nylon threads for? What? What is that in the setup? What does that mean?
So actually the nylon, let me see what I have. So these are the nylon. So actually there are two different nylon threads here. So I can show you some picture of Lynn later on if you're interested of the setup. But one thing so the nylon, these big nylon thread here is where you actually have the soap film between. So usually how we do this is like, first right now, when we start the experiments, you see these two, like these are support structure from the side. We have to remove them and we start this, everything collapse. At the beginning, you only have flow going through through these two basically touching each other. And then we have to expand that, okay? And then put it into in the model, or sometimes the model is not too big, so we can have it inserted. So the nylon, it's really give the ability kind of stretch a little bit, change, and that's why it's just simpler to use.
Okay, got it. Thank you.
No problem.
Okay. Allow me maybe ask like one or two questions, Oscar. So
yeah,
I really like the idea of nature-based solution to to address a lot of environmental issues. So I guess one of the question with respect to that is, for nature-based solution, you have to grow these trees. So how long when these trees grow from a baby tree to an adult tree, I guess?
It really depends. I mean, I have not looked too much, to be honest. I'm not a biologist. I've not looked actually too much on the growth of this, but there was a university, Nova South University, very close to us, that they actually grow they have they grow mangrove on their land. And they told me if you have the right condition, they can grow really quick. You have different quite a bit nutrients. The exact time I don't know, but they told me you have the right condition, it could grow quite, could be quite resilient and quite fast.
Yeah. So the reason why I ask this question is that it seems like a mangrove can be a very good model for sediment, to prevent erosion, and also a reconstruction of the coastline. But at the same time, I guess for the baby, when they are really small, the fluid dynamics will be completely different. Given they are have a different size, different Reynolds number, different even porosity, when they grow this. So so one thing I learned from my friend Jerry, who is also was a PhD student with Haiti, is for the seagrass, when they grow in the high speed of the water, you cannot expect them to grow instantaneously and grow them from any moment. So there may be a perfect timing for this mangrove to grow inside lab or inside a film factory. When it's ready, then being transported to the on-site. So in a way, it can be interesting from my perspective, is from the fluid mechanics perspective, when is the perfect timing for the a baby mangrove, or even some teenager mangrove, to be transported from the factory and to be integrated into the nature society and to grow accordingly. So that's the reason why I asked that question. So
I mean, that's interesting. I mean, I to be honest, I'm not really sure about the exact moment where we'll be could be transport. The couple of things that are interesting is they really have to they for them to survive, so if you see, let me show you a little schematic, at least red mangrove, one thing that they have to be in that tight zone, right? So one thing that is critical is like you're not gonna plant them anywhere. They really have to be, when there's low tide, most of their roots are exposed. In high tide, most of them are covered. One of the questions that remains with sea level rise and their issues, like, if the sea level rise happen and some of these mangroves are in that, so you see if this gonna grow, if your sea level is increasing, then you have a section where your mangrove will really not be successful. Like, you're gonna grow, so you can die. And the question becomes, what will happen with some of these? Are they gonna keep evolving maybe inland, or are they able to somehow change the topology of the sea level, right? That's some questions that are interesting. I not really don't know what might happen, but it could definitely change some of their sea level floor. So will that happen, or they will emigrate more inland? And that's something that for me, I think it's not completely clear.
Yeah, nevertheless, this is a very interesting talk, and I can see a lot also the wave, maybe the oscillator flow can also bring more sand, for this I think we are approaching to the end of the time, so thank you very much, Oscar, for.
Well, thank you. My pleasure. My pleasure to be here, and thank you for your attending the talk. It was my pleasure. So thanks.
Yeah, amazing talk. Thanks again, Oscar, and also thanks for all the people for staying late or staying early. So I will see you guys next week. So bye-bye.
All right. Thank you. Bye-bye.